Okay, right. Thank you. Well, after hearing several people saying how much what a privilege it was to open the conference, I can say that it's my privilege to really open the conference with the first substantial paper. I wanted to thank the organizers, especially Adam, for doing such a fantastic job and bringing us to this fantastic city. And especially I wanted to thank Adam for putting up with all the trouble I gave him. I wasn't sure if I could come, and he, with great wisdom, decided, well, okay, even though you don't think you can come, we'll leave you on the schedule anyway, just in case. And then it turned out it worked out, and so I'm absolutely thrilled to be here. Now, I wasn't... all right, so I was going to start with the passage from church, and then I figured, okay, I only have an hour, so maybe I won't spend some time on it, but I figured since this is the opening, we might as well, and just actually read through it. So let's start with, since this is on Church's thesis, let's start with church, with when Church's thesis sort of began its life in 1936. So Church writes, we now define the notion of an effectively calculable function of positive integers by identifying it with the notion of a recursive function of positive integers. This definition is thought to be justified by the considerations which follow, so far as positive justification can ever be obtained for the selection of a formal definition to correspond to an intuitive one. All right, so that's what we'll be talking about for the next 3 days, these 10 lines or so. Now, at the time, and for at least the next half century, there was a near consensus in the mathematical and philosophical community that Church's thesis is not subject to mathematical proof or refutation. Is even indicated by Church himself when he said, as far as positive justification can ever be obtained. So if it was a mathematical theorem, then he wouldn't have put that comment in there, as far as justification can ever be obtained. So that is, almost everyone held that, and didn't almost everyone held that Church's thesis is not the sort of thing that can be proved or refuted, and they didn't attempt to do it. All right, now what's the reason for this? Well, the standard reason people give for this is that even though computability is a property of mathematical objects, it's a property of number-theoretic functions. It's a vague and intuitive notion from ordinary language. Even one of the introductory speakers had sort of alluded to this. Now, most of the founders were thinking about what can be computed by a suitably idealized human being following an algorithm. I mean, they weren't thinking about high-speed computers back then, of course. This was 1936. So the notion of computability seems to invoke psychological notions or anthropomorphic notions. And in contrast, recursiveness is a precise property of number-theoretic functions. So the thought goes, there's no sense of proving that the one of these corresponds with the other. Now, even from the beginning, when I said it was a near consensus, it was only a near consensus that Church's thesis isn't subject to proof, to mathematical demonstration. In a letter to Kleene, Church noted that although that Gödel opposed the prevailing view, right? So again, here's this sort of much discussed letter. Now, so this is a letter from Kleene to Church about Gödel. So in regard to Gödel and the notions of recursiveness and effective calculability, the history is the following. In discussion with him, it developed that there is no good definition of effective calculability. My proposal that lambda definability be taken as a definition of it he regarded as thoroughly unsatisfactory. His only idea at the time was that it might be possible in terms of effective calculability as an undefined term to state a set of axioms which would embody the generally accepted properties of this notion and to do something on that basis. All right, end quote. All right, so it's not easy to interpret these remarks, but Gödel seems to have demanded a proof or something like a proof of Church's thesis. The idea seems to be that you do a conceptual analysis of computability and that'll suggest some axioms for the notion, and then maybe you can derive from those axioms that every computable function is recursive and vice versa. Now, whether or not Gödel at the time pursued that program or whatever, but he was soon convinced that Church's thesis is true, at least. or something equivalent to Church's thesis is true, on the basis of Turing's work. So the letter apparently was written before Gödel had read Turing's landmark paper. Now this is Gödel himself writing this is in a retrospective piece in 1946. Tarski has stressed in his lecture, and I think justly, the great importance of the concept of general recursiveness. And one has for the first time succeeded in giving an absolute definition of an interesting epistemological notion. And in a 1964 postscript to his 34 lecture notes, he wrote that, that's where the notion of general recursiveness came from. All right. So the idea seems to be that Turing's work gives a sufficiently general analysis of the concept of mechanical procedure, and that's shown to be equivalent to Turing machine. Now, Gödel's word shown here may indicate something in the neighborhood of a proof, but again, that is, he may have had something in mind that it's something like a proof, but I don't even think we need to be that meticulous in interpreting that one word. Now, the received view that Church's thesis is not subject to proof was eventually challenged by prominent philosophers, logicians, and historians. Robin Gandy and Elliot Mendelsohn claim that Church's thesis is susceptible of rigorous mathematical proof, and Gandy went so far as to claim that Church's thesis had already been proved. He cites Turing's study of a human following an algorithm as the germ of the proof. Now, Wilfried Sieg reached a more guarded but very similar conclusion. For Sieg, Turing's theorem, that's his phrase, Turing's theorem is the proposition that if f is a number-theoretic function that can be computed by a being satisfying certain conditions, determinacy and finiteness conditions, then f can be computed by a Turing machine. And Wilfried claims to have completed the project of demonstrating the equivalence via a painstaking and very careful analysis of the notions involved. So again, here's a quote from Wilfried's paper. My strategy is to bypass theses altogether and avoid the fruitless discussion of their unprovability. This can be achieved by conceptual analysis, by sharpening the informal notion, formulating its general features axiomatically, and investigating the axiomatic framework. All right, the second paragraph, in effect, is essentially the same thing. Now Gödel, it turns out, had a very similar view of things, but of course without the rigorous detail. So here's a passage from somewhere. This is from, so this is a quote from Wang's book. So this is sort of from Conversations with Gödel. So if we begin with a vague intuitive concept, how can we find a sharp concept to correspond to it faithfully, right? Which is in the same ballpark that we're interested in here too, right? We've got a somehow vague intuitive concept, and then there's the sharp one that's underlying it. And we want to somehow think that it's the concept that's underlying it, that there's only one. The answer is that the sharp concept is there all along, only we did not perceive it clearly as first. This is similar to our perception of an animal, first far away and then nearby, right? So think of the animal far away, and you just can't really see it that well, but it isn't like there's more than one animal there, and we just have to, and it's up to us which one it is. There's just one, but we can only see it in a fuzzy way, right? So we had not perceived the sharp concept of mechanical procedures before Turing, who brought us to the right perspective, and then we do perceive clearly the sharp concept. Now, Gödel mentions in the same conversation, I guess, two other cases of initially vague notions, which at least with hindsight, we can see the formal development could not have gone in any other way. I won't go through the passage. The two notions are the notion of velocity and the notion of size, right? So we have the intuitive mathematical notion of size, and then we have the precise notion, Lebesgue measure, that we have today, and then the thought is, well, look, now with hindsight, we can see that that's the one notion that's underlying the original one. Right. So it's an intriguing idea that a conceptual analysis followed by rigorous mathematical deduction can do two things. It can simultaneously approve its conclusion, and it can clear away any vagueness in the underlying concepts. showing them to have sharp underpinnings all along. Now, so this position, right, which I'll call the Gödel, Mendelssohn, Gandy, Sieg positions, just to make it short, also suggests some curious historical questions, right? And in particular, the following one. So if Turing's paper in 1936 does constitute a proof, or a sketch of a proof, or a germ of a proof, then why did so many people fail to see it that way? I mean, aren't proofs supposed to be the sort of thing that are compelling for anyone? Some prominent figures, such as Jean Porte and Laszlo Kalmar, continued to hold the Church's thesis as false as late as 25 years after Turing work was published, and even the great Roger Peter, one of the pioneers of recursive function theory, maintained some reservations. We'll get to that later. We'll get to Peter's book treatment later. So one would think that if Turing's 36 paper constitutes the seed of a proof, then the mathematicians of the day in the next 50 years would recognize it as such. Those folks should be able to detect proofs if anybody can. I mean, mathematicians are supposed to be able to recognize each other's work and, when they're pursuing their subject. Right. All right. So that's section one. Section two I'm going to go over pretty quickly. Two of my earlier papers on Church's thesis and also the Mendelssohn paper in 1990 present a number of other mathematical contexts in which an intuitive pre-theoretic notion is identified with a more precisely defined one. So the idea was to get a handle on what's going on with Church's thesis by looking at other similar cases in the history of mathematics and science. Now, the other theses are not subject to doubt anymore, nor is their status as mathematics in question. Of course, this isn't to say that they're proved, but they do serve as premises in informal reasoning, and they are central parts of mathematics. So I'm not going to go over some of the examples that I mentioned in the paper here in the interest of time. We've already mentioned two that Gödel himself latched onto. The notion of velocity, which is sharpened by the notion of derivative, and the notion of area, which it was replaced or understood in terms of measure. The notion of continuity, that's an intuitive notion that's replaced with the epsilon delta notion. The notion of proportion of magnitudes, which goes back to antiquity, right? Replaced by the common measure theoretic, the common measure theoretic resolution, and so on. All right. So Church's thesis by itself is not that uncommon of a phenomenon, and it would help to shed light on Church's thesis by looking at what happened with the other ones. All right. I'm going to get up to, All right. So new section, open texture. All right. Now, I suggest that we can gain some insight into the matter by considering a thesis of Friedrich Waismann, who's actually become lately one of my heroes in philosophy of language. One of the more neglected figures in the sort of mid-20th century, concerning empirical terms in ordinary language. The extension of Weismann's thesis to mathematics and the mathematical proof, I think, is interesting and instructive. All right, so again, I'll have to be kind of brief and sketchy here, but so be it. So let P be a predicate from natural language. According to Weismann, the predicate P exhibits open texture if there are possible objects, little p, such that nothing in the established use of big P, of the word big P, or I shouldn't have used the same letter here, or the non-linguistic facts determines whether big P holds of little p or fails to hold. In effect, the proposition P of P is left open by the use of language to date. Now, here's one of the thought experiments Weismann uses to characterize this notion. Suppose I have to verify a statement such as there is a cat next door. Suppose I go over to the next room, open the door, and look into it and actually see a cat. Is this enough to prove my statement? What should I say when that creature later on grew to a gigantic size? Or if it showed some queer behavior usually not to be found with cats, say if under certain circumstances it could be revived from death, whereas normal cats could not? Shall I, in such a case, say that a new species has come into being, or that it was a cat with extraordinary properties? The fact that in many cases there is no such thing as a conclusive verification is connected with the fact that most of our empirical concepts are not delimited in all possible directions. Now, the last observation in this passage is the key. Our empirical concepts are not delimited in all possible directions. And I would add that, this is me now, that neither are some of our mathematical concepts. Now, Mark Wilson's onslaught against what he calls the classical picture of concepts in his most recent mammoth book, 2006, is of a piece with Weissmann's thesis here. What Wilson calls the classical picture is that our concepts are somehow precisely delimited in all possible directions. And if you understand a word, you know in effect how the word applies in all possible circumstances. So the attack against that is of a piece with Weissmann's notion of open texture. Now, the phrase open texture doesn't appear in Weissmann's treatment of the analytic-synthetic distinction in an article published serially in Analysis, but the notion, or a closely related one, clearly plays a central role there. Right? So it's curious that this series of papers, again, which is, I think, much neglected in philosophy, coincides with Quine's attack on the analytic-synthetic distinction. Exactly. Two Dogmas was published in 51. But Weissmann's take on it is in some ways similar, but very different. Unlike Quine, he is allowing an important role for analyticity and all right, anyway. Weissmann observes that language is an evolving phenomenon. As new situations are encountered and as new scientific theories develop, the extensions of predicates change. As new cases are encountered, the predicate in question is extended to cover them one way or another. When things like this happen, there is often no need to decide and no point in deciding whether the application of a given predicate to a novel case it represents a change in its meaning or the discovery concerning the term's old meaning. The contrary thesis, the idea that there's one and only one way to go on, no matter what comes up, that's the classical picture that open texture and is opposing. As Weissmann writes, simply to refer to the ordinary use of a term is naive. The whole picture is in a state of flux. One must indeed be blind not to see that there is something unsettled about language, that it is a living and growing thing, adapting itself to new sorts of situations, groping for new sorts of expression, forever changing. Now, I submit that the same goes for mathematical languages to some extent, obviously not as much, but to some extent. Now, the official definition of open texture in this 68 paper, I realize we're sort of taking things out of order here. The analytic synthetic paper was in the 40s and early 50s. I'm not sure when the open texture paper was actually written. It was published in 68. But the official definition limits it to the application of predicates to cases that had never been considered before, right, as indicated by the thought experiment and about 10 other thought experiments that Weissmann gives. But the dynamic nature of language goes well beyond that. He illustrates the point, Weissmann does, in some detail with the evolution of the word simultaneous in light of development in relativity, in science. The main innovative theses of the theory of relativity actually violated the previous meaning of that word. Right? I mean, it wasn't part of the meaning that there's a relativity in it, in words like before, after, at the same time as. So how do we understand the linguistic fallout of that theory, right? So we just say that a brand new word with a new meaning is coined with the same spelling as an old word, that the word simultaneous now means something different now than it did in 1890 or whatever, right? Or do we want to say that the old word now has a new application, or we were wrong about what the old word meant? Now, according to Weissmann, that's a bad question. There is no need and no reason to decide what counts as a change in meaning and what counts as the extension of an old meaning to new cases, going on as before, as Wittgenstein might put it. Even though, again, to sort of contrast where we're going to go with Gödel's view, even though there really was only one way it could have gone, right, given the scientific development. Weissmann said in an earlier installment in the series, the analytic synthetic paper was actually written serially. There are like six short articles published in Analysis, And each one of them ends with to be continued. By the way, including the last one. So if you actually look, right, it's like kind of waiting, when the next one is, but I think we're still waiting for it, right? Anyway, in the earlier installment, he wrote, there are no precise rules governing use of words like time, pain, and so on, and that consequently to speak of the meaning of a word and to ask whether it has or has not changed in meaning is to operate with too blurred an expression. Now, the question I want to ask now is this. Are the standard terms of mathematics exceptions to Weismann's account of language as in flux? He never gives mathematical examples. To some extent, yeah, they are exceptions. Like consider the notion of a prime natural number. All right, now strict finitism aside, I don't think there's much room for any open texture there. I mean, we actually prove that every number is either prime or composite. But I think that's more the exception than the rule, right, in mathematics as practiced. Think about the word number, right? Originally, so there are natural numbers, and then we extend that to real numbers. All right, those are numbers, complex numbers. Now, clearly, at some point, whether complex numbers count as numbers must have been, again, I don't know much about the history of this, but that must have been in doubt at some point. Otherwise, why are we calling them imaginary numbers, right? The use of the word, by the way, the use of words there is rather curious, isn't it? So we have the natural numbers. All right, that's cool, right? Then there's the real numbers, all right? But then there's there's negative numbers, right? Some doubt about those, negative, right? Then there's irrational numbers, and now imaginary numbers, right? Now, of course, there's something misleading nowadays about the word imaginary. I mean, whatever your philosophy of mathematics is, there isn't going to be much difference between I and 6, right? One's real and one's imaginary, but at least at some point there must have been some doubt. Otherwise, that word wouldn't have become common. All right, and extending even beyond, like, do quaternions count as numbers? Again, so that's the sort of question that Weismann would say that it's just a bad question to ask that. All right. All right, so not so much for open texture. Now another one of my heroes would talk about Lakatos. Okay. So before getting back to computability, let us briefly re-examine Lakatos's favorite example, developed in delightful detail in his monograph, Proofs and Refutations. All right, so that monograph presents a lively dialogue involving a class of rather exceptional mathematics students. The dialogue is a rational reconstruction of the history of what may be called Euler's theorem. Again, I don't know if Lakatos is getting the history right, but again, and that matters, but I'm not sort of in a position to, and it's not presented as history, except in the footnotes. All right, so here's Euler's theorem. Consider any polyhedron. Let V be the number of its vertices, E the number of its edges, and F the number of its faces. Then V minus E plus F is 2. All right. Now, the reader of the book is invited to check that this equation holds for the usual kind of polyhedra you might think about. So you think about cubes and tetrahedra and icosahedra and stuff like that, right? And you'll see, oh yeah, it works, right? Just, work it out, each one, how many faces, how many edges, right? All right, so naturally, you have sort of inductive evidence that this is true, and you'd like to see that either confirmed by a proof or refuted by a counterexample, and Lakatos, in a delightful way, gives us both. Proofs and refutations, right? All right, now the teacher begins with a proof. All right, again, if we had more time, I'd go over this in some detail, but here's apparently how it goes. So take a polyhedron, remove one of its faces. It'd be nice if I could if I had, right time for this, I'd draw little pictures and, we go through it, right? So take a polyhedron, remove one of its faces, take what's left and stretch it out and put it on a blackboard. So now it's on a single surface. Then add lines to triangulate it, right? To make it into a bunch of triangles. Notice that whenever you draw a line, right, to triangulate it, you're adding an edge and adding a face, right? So that'll leave V minus E plus F constant, right? So after it's triangulated, then you move the edges one at a time. And notice that every time you take an edge away, you're taking away an edge and a vertex, right? So again, V minus E plus F is going to be constant. So you keep doing that till there's only one triangle left, right? So then you have three vertices, 3 lines, 1 edge. V minus E plus F is 1. Then you remember the face you took off, right? And that becomes 2, right? QED, right? All right. Now, All right, so that's the proof. Then the class, again, in Lakatos's reconstruction, considers counterexamples to Euler's conjecture, right? So then they start thinking of refutations. So one of them comes up with a picture frame, right? So think about that. All right, now that one, when you try to stretch it on a blackboard, you won't be able to do it. Or what else do they consider? A cube with, so consider a cube, but where there's like a cube in the middle of it that's missing. Sort of like a donut, but sort of shaped into a cube. No, not like a donut, but it's a cube, and then there's a hole in the middle that's cube-shaped. Right. So then V minus C plus F is going to be something else. And then there's what he calls a star polyhedron, where you've got like a cube with little cones stuck around it. Right. Now, none of these things fit Euler's definition. All right. So then at this point, not definition, none of those fit the proof. Right. That is, V minus C plus F is something other than 2. Now, the dialogue starts to get interesting at this point, all the more so because it's supposed to follow some trends in the history of mathematics. So some of the students just declare that the counterexamples are monsters, and they don't refute the theorem. So, oh, well, that doesn't count, and leave it at that, right? They're not really polyhedra. Now, again, we were told before that philosophy is too important to be left to the philosophers, right? So there's some philosophy bashing, right? Which I can participate in good conscience, because I'm one of them. So a philosopher in the crowd might argue, right, at this point, right, that, well, I've done a conceptual analysis of polyhedron, and those don't count. Those aren't it, right? Now, one way might be to say, okay, I'm just going to define a polyhedron to be a figure for which this proof works. So then the proof, in effect, just becomes a stipulative definition. A second maneuver is to restrict the theorem so that the proof holds. So you might say that for any simple complex polyhedron, V minus C plus F is 2. A third line is to take the counterexamples to refute the theorem, and then declare that the notion of polyhedron is just too complex and unorderly for decent mathematical treatment. A fourth line accepts the counterexamples and then looks for a generalization to cover them, right? A generalization of Euler's theorem that will cover the counterexamples and the original ones. Now, the situation in Lakatos's dialogue, or better, the history that it reconstructs, I think really nicely illustrates Weissmann's account of language, of the notion of open texture. Even though it's mathematics that's at stake here, I mean, this is mathematics if anything is, it's geometry, and not ordinary empirical words from ordinary language. The start of the dialogue refers to a period in which the notion of polyhedron had an established use. That is, this is not a stipulative definition, right? The word had a use. Nevertheless, it had no definition, right? No stipulated formal definition that everyone would agree to. Surely a necessary condition for a figure to be a polygon is that it be bounded by be a polyhedron, is that it be bounded by polygons, plane polygons, but there was no generally established sufficient condition for being a polyhedron. All right, so in short, what I want to suggest is that for the mathematicians at the time and previous generations, the notion of polyhedron was governed by open texture. Right? There were just cases that when they came up, just wasn't clear whether they could be applied. Now notice that did not prevent them from proving theorems about polyhedra. Right? You don't need the precise definition. Think about there are theorems from antiquity about polyhedra. The old theorem that there's exactly 5 Platonic solids. Now, when the cases did come up, right, the cases that did challenge the notion, a decision had to be made. And as Lakatos shows, different decisions were made or different decisions were proposed. Now, at the end of the dialogue, a most advanced student proposes a purely set theoretic definition of polyhedron. So accordingly, right, according to this advanced student, the history is jumping ahead by centuries now, a polyhedron is just a set of things called vertices, edges, and faces that satisfy certain general conditions. The general conditions are specified. And then he goes on to show that under certain of those general conditions, the polyhedron is Eulerian and certain conditions not. Now, you might claim now, and it does seem to me to make sense, that this final austere and rigorous set theoretic definition of polyhedron is not subject to open texture. In fact, it's been nailed down now, just like the notion of prime number, right? A prime natural number has been nailed down. Its boundaries are as determinate as you can wish, or at least so it appears. But this is not to say that the original pre-theoretic notion of polyhedron was similarly determinate, nor that the new one exactly matches the old one, right? There was some sharpening going on. And I think this is yet another example of the same sort of thing as Church's thesis. And now I'm ready to resume the main theme, right, after this bit of these two sidetracks, right? One through Weissmann and one through Lakatos. All right. Now, the main question then concerns the so-called intuitive or pre-theoretic notion of computability, or effective calculability, to use Church's word, and its relation to recursiveness. So I take the suffix, again, I'm not claiming that this is a philosopher's conceptual analysis, but I take the suffix at the end of that, able, able, computable, calculable, right, to be something like capable of, or it's possible to calculate, it's possible, it's capable of calculation. To say that an item is edible is to say it's capable of being eaten, presumably without toxic effects. Right? To say that a number theoretic function is computable is to say it's capable of being computed. Now, typically, this modal construction, the ABLE construction, is sensitive to the interests of those speaking or writing. It's context sensitive, in effect, and to the background assumptions. Right? So, to take an example, suppose that a distance in time is runnable by a person, R-U-N, runnable, right? By a person if she can cover the distance in the given time on relatively flat ground by running. All right. Now, is an 8-minute mile, do I need to tell you what a mile is? Right. Is an 8-minute mile 1.3 kilometers runnable by me? Right? Is that distance runnable by me? Well, it depends on what exactly is being asked. If I were to warm up right now and go out and run a mile as fast as I can, it will probably take me longer than 8 minutes, probably actually 10 or 11, and that'd be on a good day. So in that sense, an 8-minute mile is not runnable by me right now. On the other hand, if I were to spend 6 months on a training regimen, which would involve working out diligently with a trainer 4 or 5 days each week, losing about 30 pounds, and avoiding injury, I could probably do it, because I used to do it. Like 20 years ago, I could run a mile in 8 minutes. So I could probably manage it again. So and I'm probably capable of that regimen as well. I mean, I think I could do it. I think, right? The injury part is the thing that gives me some doubt. But all right. So in that sense, an 8-minute mile is runnable. All right. So before I said it isn't. Now I'm saying it is. Right. In general, it depends on what the parameters are. Right. All right. Now, so what are the corresponding parameters for the pre-theoretic notion of computability? What tools and limitations are involved in that? Now, I would suggest that in the 30s, and probably for some time afterward, the concept was not delimited with enough precision to decide every possible consideration concerning those things, tools and limitations. In other words, computability exhibited open texture. And as with Lakatos's example of a polyhedron, the mathematical work, notably Turing's argument in 36, and the efforts of other founders, people like Church, Turing, Post, Kleene, Pater, sharpened the notion to what we have today. So I'm sort of honing in on the word that Wilfred used in the early paper of sharpening the notion. In other words, the mathematical work served to set the parameters and thus to sharpen the original pre-theoretic notion. Now, Turing's own work, this is something that most scholars here don't need to be reminded of, but a lot of people in philosophy and elsewhere do. Turing's own text makes it clear that he focuses on computation by a human being. Following an algorithm and not, say, by a digital computing device. It's amazing how many people seem to think you're talking about, digital computers, as if there were a whole bunch of those things around in 36, and that's what he was talking about. Now, following Sieg, let's use the term, this isn't going to help much in the oral part. Let's use the term computer, spelled O-R, to designate a person engaged in computation. Right, so computer, you know what a computer ER is, that's one of those things, right? But this is a person engaged in computing. So our question is, what tools and abilities do we allot to the computer in characterizing the notion of computability? Just like with the notion of runnable, what tools and abilities are we going to focus in on? Now, some of the theses that I'm interested in here can be illustrated with the so-called easy half of Church's thesis, the kind that very few people ever doubted. The statement that every recursive function is computable. So here we actually confront what are now some standard issues of feasibility, right, of computation. All right, so again, if I had more time, I'd go over this in detail, but I didn't put it on the slide. So think about an Ackermann function, which is recursive, But so the typical Ackermann function, or atypical Ackermann function, if you take with very small inputs, like f of 5 and 5, the output is going to be larger than the number of particles in the known universe. So this is a function that grows really fast. So is this function computable? Well, I challenge anybody to compute it, right? I mean, you're going to run out of universe, right, if you try to convert this, right? It's just a matter of running out of time and then dying, right? There just aren't enough particles in the universe to calculate this thing, right? All right, so now in as late as 1960, Porte presented another example of a horribly infeasible recursive function and concluded that it is not humanly computable and therefore not effectively computable. Because remember, we were talking about what a human can do, right? What a human can compute. Now, as Mendelssohn put it in a review. Now, of course, the situation is pretty standard now, and so's the response. Mendelssohn, again, had no trouble dismissing the example, as he put it in a review of this in 1963, in a review of Porte's paper in 1963. Human computability is not the same as effective computability. A function is considered effectively computable if its value can be computed in an effective way. Again, I won't bother reading it out. Again, you all know the drill on this. In other words, the notion of computability invoked in Church's thesis involves idealizations on the abilities of computers. And these are standard idealizations in mathematics, and they've been invoked since antiquity. I mean, think about, like Euclid's postulate, two postulates. The first one, to draw a straight line from any point to any point. Euclid does not say if it's not too long, right? You can draw a straight line from any point to any point, right? There's no limit as to how long the ruler is, right? You're allowed to use. All right, still, I think it has to be admitted that the idealization, especially the one that we've settled on today, is a sharpening of the pre-theoretic notion. Otherwise, people like Porte would be charged with just being confused and not knowing what they're talking about as late as 1960. And notice that since we're idealizing anyway, you can idealize even more than we in fact do. I mean, why are we limiting it to only finite states or finite amount of time? If we allow infinitely long algorithms, then every function is computable, right? Of course, that's not a very interesting notion, but still, why that one? Why that idealization? Now, I'm not saying it was a bad idea to pick the one we did, but it's just not quite settled what the idealization was in the 30s and 40s and 50s even. And the fact that we're idealizing, even then, that doesn't sharpen it all the way to recursiveness, using hard rails to use the Wittgensteinian term. There's still some open texture. An idealized person considered in isolation, so you have a person who's calculating, they're probably a lot more like a finite state machine than a Turing machine. Because there's still going to only be a finite amount of memory available for them to write stuff down on and so on. And it might be reasonable for some purposes to set some fixed bound on the idealization, like polynomial time, exponential time, or something like that. Now, I'm not claiming that the current concept is incoherent, nor that once it's formulated, it corresponds exactly to recursiveness. Church's thesis is certainly true, but this is not to say that the original pre-theoretic notion was as sharp as that. Sharp as all that. Now, in the later article, Mendelssohn, wait a minute. Yeah, I think this is the right slide. Noted, all right, so again, this is Mendelssohn's paper where he argues that Church's thesis is the sort of thing that is subject to proof. And he gives an example of the easy half of Church's thesis, right? So the so-called initial functions are, all right, so again, this is a quote from Mendelssohn. This is, again, and I think I can't but agree with this. This is about as good an example of a proof as you're ever going to see. Consider the proof of the easy half of Church's thesis, which also you'll see, by the way, an instance of this even in Church's article, the 36 article. The so-called initial functions are clearly computable. We can describe simple procedures to compute them. Moreover, the operations of substitution and recursion and the least number operator lead from computable functions to computable functions. In each case, we can describe procedures that'll compute the new functions, right? So again, by induction, then, every recursive function is computable. Now, I might add that this argument, or something like it, seems to have convinced just about everybody, almost everyone, not Porte and so on. And nowadays, again, if you know when you're teaching this stuff, right, you present this argument, and students will usually find it convincing. Nevertheless, I submit that the proofs like this one help to sharpen the notion, right? And again, this is not that different from the Lakatosh example, where you look at Euler's proof, and that helps us to sharpen the notion of polyhedron. So we look at the proof, and we see that the proof itself is not taking any count of feasibility, right? When we're doing proofs by induction, then we don't really care how many steps we're running together, right? Although the finiteness condition is, in effect, is also sort of implicit in the proof. So a study of the reasoning in Mendelssohn's argument shows us what the idealization from actual human abilities are, or where they're supposed to come in and what they are. All right. Now, with Weismann, I don't see a strong need to adjudicate disputes concerning which formalized notion gives the true essence of the intuitive notion. To even ask that question is to operate with too blurred of a notion. Now, this is a bit of an aside, but I guess I have time for it. So Wittgenstein is notorious for saying that mathematical proofs somehow fix the sense of what's proved. And then he gives an awful lot of really, I think, dumb examples. Claiming that in arithmetic, you're sort of fixing what you mean by number as you're proving things. Now, with the examples that he's sort of honing in on, it strikes me that the thesis is crazy. Think about, just to take a spectacular example, from the proof of Fermat's last theorem, right? That doesn't tell us in any way what we mean by natural number and exponentiation and so on. I mean, the proposition means the same thing to us as it did to Fermat, even though you have to do this complicated detour in order to prove it. So in some cases, when you try to apply this Wittgensteinian thesis that proofs tell us what we mean, right, it's silly, right? But in other cases, though, it's less silly, and this is one of them. By studying the proof and by studying, in effect, why it is we find it so convincing, that, in effect, tells us what we mean, right, or what we're going to mean, right, from by the concepts and words in the proof. All right, now let's turn finally to the harder half of Church's thesis, because there's a similar lesson to be there, and then I'll finish with this one. So, and again, this is the at one time much discussed Kalmar paper, and it will also, as I promised, come back to a Roja paper too. So in 1959, let me see which slide we're on. Oops. Right. So in 1959, Kalmar accepted the near consensus that Church's thesis is not a mathematical theorem, which can be proved, but then he came to the opposite conclusion of everybody else, suggesting that Church's thesis is false. And he gave a plausibility argument against it. And here's Kalmar's counterexample. Put that in scare quotes. So define the improper minimalization of a function f to be the function f prime, which is the least number, if there is one, for a function f x y. If there is one, otherwise it's 0. All right, so again, all right. Now let psi be a recursive function whose improper minimalization is not recursive. Again, it's an easy exercise to find such a one. Now, Kalmar proposes the following method to calculate the value of psi of p, right? The improper minimalization of this other function. That should be a phi, not a psi. All right. So anyway, calculate the p0, p1, p2, right? In order, looking for a 0, right? So you got to do two things at once, but that's sort of common in recursive function theory. One is you look for a counterexample. You look for the example of the minimalization. And the other is you try to prove the theorem that there isn't one, right? In effect, so do a little bit of each, the usual dovetailing that you do with calculability. So spend like 10 minutes looking for an example, and then spend 10 minutes trying to refute it, show that there is one, 10 more minutes looking for one, 10 minutes refuting it. Now Kalmar notes that this method won't compute the function unless you can refute every function of the right form, every theorem of the right form, but he says that that's plausible, that you can do this, right? It's kind of an optimism that was sort of prevalent at the time. Now, I'm not suggesting here for even 1 minute, right? Don't get me wrong here, that there's some sense in which Kalmar's method counts as an algorithm, right? Church's thesis is true, right? But even at the time, Even at the time, Mendelssohn had no trouble dismissing it. But is there something, here's the question though, is there something unambiguous in the pre-theoretic notion in use in the 30s that rules this out? Now, and here's a sort of an exegetical question, right? If it's so obvious that this function, that this method doesn't count as an algorithm, then why did Kalmar think that it did? To say the least, he was an intelligent thinker, not prone to deny what's obvious. I mean, his paper was accepted in a mainstream logic journal, right? So it couldn't have been that this is just stupid, right, on his part. What is it that's all right? Now, what I want to suggest again is that at the time things were not as clear as they are now. There's no problem. We have no problem dismissing the example now, but at the time, right, things weren't quite as clear. So chapter 19 of Pater's landmark textbook at least tentatively endorses Kalmar's argument, tentatively. The next chapter turns to Church's thesis. Again, I won't have time to, I'm not going to sort of read out what she's saying about it. But you would think from what she says that Kalmar's method is disqualified as an algorithm. Different mathematicians will respond differently to the instruction, try to prove such and such a theorem. Remember, the instructions for the algorithm were look for a counterexample. All right, that's effectively, and look for the example. I keep saying counterexample. Look for an example, that's clear enough. But then try to prove the theorem, right? Now, different mathematicians are going to respond to that in different ways, right? And no one's claimed that process can be mechanized. Matter of fact, we know it can't be, given by what we mean by now by mechanism. Still, Pater doesn't object, at least not yet. She goes on to give a detailed, painstaking analysis of computation relating the notion to Turing machines. And then the chapter closes. If we assume that the concept of a function calculable by the aid of a Turing machine, we have succeeded in capturing the concept of the most general number theoretic function whose values are everywhere calculable, then the results obtained above in fact characterize the general recursive functions as the functions calculable in the most general sense. And under this interpretation, the function, Kalmar's function, is an example of a function not calculable. All right, so far so good. So she actually now has an argument against the Kalmar's method. In particular, even though it tells the mathematician what to do, right, you tell him what to do. Try to prove this theorem. I mean, this is what mathematicians are trained to do. So it isn't like like he has no idea what you told him to do. He says, look, here's your instruction, right? Here's in the algorithm. Try to prove this theorem, right? That's what we train students to know how to do in math, in math PhD programs. So it isn't like he doesn't know what to do, but different mathematicians will respond differently to that construction, to that instruction, right? And for algorithms, you need to be able to be told what to write down explicitly in each step. All right, so far so good. But notice that she does say if, right? She says if we assume that the concept is, has been analyzed the way that we said, and not only that, but she hedges, right? That is, her conclusion isn't what you think. It isn't the same conclusion you would see in a textbook today. She writes, but however plausible it may seem that this interpretation correctly reflects real mathematical activity, we are nevertheless dealing here with a certain demarcation of the concept of calculability, and the future evolution of mathematics may bring about methods of calculation completely unexpected nowadays. Now, Weismann could not have put it better. Pater declares that at the time, the notion of, and this is the time now is 1957. At the time, the notion of computability was still, oh, by the way, in 1957, Studia Logica was 5 years old. So at the time, when Studia Logica had its 5th birthday, was just heading off to kindergarten for the first time, she declares that the notion of computability was still subject to open texture. I mean, not using Weismann's word yet, because Weismann's word hadn't been invoked for another 11 years after that. Or at any rate, she did not feel herself to be in a position to rule out any further sharpening of the notion. Now, in the ensuing decades, to conclude, the community of logicians has come to see the notion of computability as sufficiently sharpened. It's now reasonable to hold that Church's thesis is established, if not proved. More recently, Turing's argument has been supplemented and extended in the deep analysis by Gandhi and our own Wilfried Sieg. In effect, they fulfilled Gödel's suggestion way back at the beginning of this talk I mentioned, namely, to state a set of axioms which would embody the generally accepted properties of this notion and to do something on this basis. Right? In sum, then, the notion of idealized human computability is now about as sharp as anything gets in mathematics. Right? There is not much room for open texture anymore, or so it seems. Anyway, right? The present conclusion, my conclusion, is that the notion of computability is in use now is the result of the last 70 years of examining texts like Turing's, of reacting to proofs and refutations, to use Lakatos's term, and of the overwhelming success of the theory of computability, of recursive function theory. It is not accurate to think of the historical proofs and related theses as establishing something about absolutely sharp pre-theoretic notions. Rather, as remember Gödel's metaphor of like looking at an animal from far away, and then as you get closer, you see that there's, that it's actually really sharp. I don't think that's the right metaphor to use. Rather, the analytical and mathematical work serve to sharpen the very notions themselves. Once again, though, this is the norm in mathematics. Thank you.
Oh. So we have 10 minutes time for question. Could you please sit still?
This Weissman thesis that every notion, and he has no mathematical examples, so he speaks language. Yes, it seems to me that he is breaking hard into an open door. I cannot imagine anybody arguing with this. Was there what they call classical point of view? Is there any name? Is there any name that anybody defended the other point?
No, because it's more like it was more of a presupposition than. Let me go back. Yeah, it was more of a presupposition of how things were done, and even today you see versions of it, certainly in philosophy. Again, I've been doing a bit of philosophy bashing, but these sort of conceptual analyses, right, don't seem to take the notion of open texture seriously at all.
I think any linguistic book will confer any. Take Jasperson or Jasperson.
Yeah, they might, when you sort of put it that way. Of course, this is now, right? Not back then. This is, this is before there was a science of linguistics. But even now, if you look at the work, like with say, Montague grammar and so on, where they're actually giving truth conditions. So you want to say like X is P for some P, if and only if, and then you write something down on the right. It seems like that's presupposes that there isn't going to be any room for doubt, no matter what cases come up. Mm-hmm. Yeah, Weissman did take himself to have real opponents. I don't know why I'm walking around, but.
So one historical remark, Weissman introduced this concept in 1945.
45.
Yeah, in the paper about verification, and he criticizes.
Oh, you're right. I was mixed up. It was only published in 68.
Yeah. No, it was published in
45?
45, yeah.
I
think in Proceedings of Aristotelian Society, but
I'll get the reference from you. Is it the same paper that
yes.
that has the 68?
Yes,
so it was just reprinted in 68.
Yeah, and he repeated this several times in language straight. But there is one problem with interpretation, because one interpretation is that if you have an open texture, a concept with, or term with open texture, so you can sharpen, but it remains still open or vague or something like that. And the second interpretation is even stronger, that any expression which you use to sharpen is still open.
Yes.
So I guess that the second interpretation is very difficult to maintain for mathematics.
No, I agree with that completely.
Yeah, so...
Right. So the question or the point to repeat it is that there's sort of two interpretations of the original notion of open texture. One of them is that it's a temporary notion, that you can eliminate it by sharpening the notion completely. And the other interpretation is that you can sharpen, but you can never completely sharpen. Yes? When it comes to mathematics, at least it seems to me make more sense that you can completely sharpen. if not the notion of computability, although that's probably a good example of any, think of the other example I gave of a prime natural number, right? I mean, I can't imagine any room for, who knows, right, what someone's going to come up with, but it seems to me intuitive that there's just no room for open texture there anymore. Whereas with empirical notions, it does seem to make sense that no matter how much sharpening you do, there's still going to be some open texture.
So I'll advocate for the crazy, unpopular view that nobody believes. So Putnam, in a few places, both in discussing philosophy of language and in discussing philosophy of mind in the context of computability, he says that we have to hold on to something unlike the open texture view in order to make sense of scientific discoveries and the idea that, you take your historical figure who has different concepts. How could, in principle, we can always explain the discovery, and they would accept it. So you take Archimedes, you bring him to the present, and we all believe that he's going to agree with us about physics, chemistry, if we just sit him down and explain it to him. He's not going to say, you have different concepts than me. So the communicability of scientific discovery across paradigm shifts, whatever, this presupposes something other than a change in meaning. And so I was wondering if you have a
I just don't agree with that. I mean, obviously, to some extent, if you were to sort of bring Turing back, and hypothetically, there'd be a big meeting on Turing. We can discuss this hypothetical in next June. But if you were to bring him back and say, "Look, here's what we're up to now," is that what you had in mind? It just seems on the blindly obvious. You'd say, "Yeah, of course, that's what I had in mind," right? And maybe the same thing applies to Archimedes. Who knows? I mean, you'd have to teach him English first, and right. But at least you wouldn't have to do that with Turing. But even so, I don't think that's still quite the same thing as to say that they could see that that's the way it had to go, that's really the way it was back then, and that it was known back then that that's the way it was. So I just don't agree with Putnam's analysis here. Right. So what I should be giving shorter answers to these, huh? So we can. All right. Either that, or I should have given a shorter talk.
You mentioned that when set theoretic definition of a polyhedron is given, the open texture disappears. But I mean, this hinges on the assumption that our notion of a set,
of course,
is devoid of open texture. I mean,
yeah.
Is that the case? I mean, how does that relate to, say, continuum hypotheses and such?
That's right. That's why I even hedged a little bit, where I said it seems to me that there isn't much room for open texture. But the question would be whether, if there is some remaining open texture in the notion of set, whether that's going to affect what's going on with the recursive functions. And it looks like it isn't, but who knows? I mean, in effect, you can't ever be sure in advance that you've eliminated all possible open texture. But and that's in effect not unrelated to Weissmann's point about even when you sharpen a notion, you got to use words to sharpen it, and those words themselves, might be subject to open texture. Right. Should we just skip the next talk and? Okay, right, all right.
Open text.
Right. Well, Stewart, thank you very much for putting my name next to Gandhi's, but we don't share the same view.
Oh, I know that, right.
But in any event, I was wondering, for many people, confluence of notions in the 30s was very important as support for Church's thesis.
Yes. Mm-hmm.
What does it has an effect on open texture, the confluence of
Yeah,
mathematical notions?
It would suggest that this was the reason why we settled on a single notion, and the particular one that we settled on. Right? So the fact that all these different notions all seem to converge on the same one is good reason to think that this is that we did what we should have done. Right.
From your talk, I got the impression that you think that now it's very clear to everybody what church thesis says. Mm-hmm. According to my experience, it's completely false. Even the debate between Penrose and Lucas and others say that the people understand differently even the content of church thesis, whether it applies to single person, what single person can compute, or single computer can compute, or the all human past, future, present, can, and also assume that we understand what is the notion of function,
yes.
from natural numbers, which of course many people who are not Platonists think they do not understand. So I was present in so many debates and arguments not in the 50s, 60s, but in the 21st century about the content of church thesis, so I don't quite sure what this confidence is based.
That's, I think, if I'm understanding it right, that's more grist for my mill. That is, that since there are different ways of sharpening the notion, the intuitive notion, and they may not come to the same thing extensionally. That would be like, so the example you gave is, you're talking about a single computer, a single person working in isolation, presumably Turing was, or seemed to be, or you're talking about the community of computers, and once machines get involved in it, which they are in a lot of contemporary discussions. Are you talking about machine computability? Are we allowed to bring in weird facts about the laws of physics and space-time loops and stuff like that? The randomness in nature, right? All this, I think, is grist for the mill. That the notion it would, at least was at one point subject to open texture, and I guess your point is that it still is. Yeah.
We have 3 questions on the list, so I think it will be our time. It will exhaust our time.
How about if I just don't answer them? If you just ask the questions, then we can. How about if I just don't give answers? Then we can get it. Yeah, right. Okay.
3 questions, 3 answers. Paula Quinion, please.
Okay, so you agreed with Rafał that there is no space. There is a space for open texture in set theoretical notions. But what about natural numbers? You just said that there is no.
I doubt it. Yeah.
But what about the debate between yourself and neo-Phrygians?
Oh,
then?
Yeah. Well, I'm kind of a rampant extensionalist there. I mean, that's more concerning what the right analysis is, but I don't think I think maybe a more relevant debate might be between us and intuitionists and the like, where you're actually getting different theorems, and as to whether those are still debates over the same notion, as opposed to, in effect, what's the right philosophical underpinning behind them.
So your bottom line is it provable, Church's thesis, or is it sharpenable?
Both. That is, the notion of proof. The notion of proof is sufficiently open textured.
Oh, okay. Okay.
Right.
May I ask for a clarification of the open texture thesis? Namely, you said that the concept is not limited in every possible direction as the essential characterization. Do you mean it's a kind of temporal flaw, something to be, sooner or later avoided, or at least the ideal of removing this?
No,
or it's something, the very essence of the language.
It's the very essence of how, again, I'm interpreting Weissmann here, and apparently people here may know him better than I do. But it's of the very essence of language use that this notion that this is always going to be with us.
Okay.
It's
so
not a defect.
It answers
right.
his question.
Yeah.
I mean that we'll find a number of writers, including Frege, Carnap, and so on.
Oh, I hadn't thought. Yeah, that's right. When you're looking at opponents, actually, that should have just popped right in my head. Yeah, Frege. Yeah. So, yeah. So the answer to Yuri's question is Frege. That's who the opponent is. No, well, the mathematics is the ideal, but he certainly gave a lot of natural language examples, especially when he sort of turned to philosophy of language later on. His logic was focused in on mathematics. That's certainly right. You're right. So the Weissmann thesis is that it's here to stay. This is not something that we're once we figured out how to really speak, we can get rid of it.
Okay, thank you very much. Our time is over, so thank you.